Welcome to Unit 3 Solutions, Section D, Colligative Properties. This is the last section of our lecture notes. Colligative properties are going to be properties that are based on the number of particles and not the type of particles. So these are things that what's important is that there's pieces there disrupting the normal pattern that you would see interactions between the particles of a solution typically, and not necessarily what type of particles they are. So it's the number of pieces. So if we look at a quick diagram of what happens, if you have your pure solvent here, and these particles can interact with each other, there's a certain amount of intermolecular force. They have a certain rate at which they can evaporate and move in their vapor pressure. When you put a non-volatile, so one that's not just going to evaporate out quickly, non-volatile solute in there, those pieces get in between and interrupt and change the way the pieces of the solvent interact with each other. And that's going to change their properties. There's only two colligative properties that you're responsible for knowing, and those are boiling point elevation and freezing point depression. So quickly, just review of some basic vocab. Elevate versus depress. When we elevate something, you have to elevate your foot. When you heard it, you use the elevator. It means to raise something up. When we are depressing something, you depress the stopper, you depress the accelerator pedal or the brake pedal in your car. That means to push down. So like a tongue depressor when you go to the doctor's office and they push your tongue down so they can look at your tonsils. Elevate, raise up. So if it's boiling point elevation, boiling point elevation, if we add particles, the boiling point goes up. The more particles we add, the higher the boiling point gets. So if we're talking about water, if I add a bunch of particles, the boiling point will be higher than 100 degrees Celsius. We talk about freezing point depression. So if I'm adding particles, the more particles that I add, the lower the freezing point gets. So if we're talking about water, water freezes at 0 degrees Celsius. I add a bunch of particles. It has to be colder than 0 degrees Celsius to freeze it. That's the big concept here. Boiling point elevation. If you memorize that goes together. Boiling point elevation goes together. To elevate means to raise up. For every mole of particles, we raise the boiling point of our solution by 0.52 Celsius. Why aren't you writing there? 0.52 degrees Celsius. 0.52. That's a huge typo. Please fix it in your notes. For every 1 mole of particles goes up by 0.52, a half a degree. It's important to know that it's that small because one of the things that you'll see in a lot of reference materials or review books is that this is the reason that we add salt to our food when we're cooking. But sodium chloride, which is the majority of the salt that we use when we cook, dissociates into sodium and chlorine in water. We saw that back in Lecture A. So for every 1 mole of sodium chloride we put into water, we get 2 moles of particles. So for every 1 mole we put in, we get 2 moles out, which means we're going to multiply our 0.52 by 2, and we would raise the boiling point of water by 1 degree Celsius. So how much is 1 mole of sodium chloride? Well, if we use the gram formula mass, 1 mole of sodium chloride is 40 grams. So 40 grams of salt in 1 liter of water is pretty salty water, and none of us use that much salt when we cook, unless maybe you're using salt potatoes. But even then, you're not going to significantly raise the boiling point of the water to a point where you're cooking your food any faster. The salt in your food when you cook is only there for taste. Boiling point elevation, you would have to have a pretty concentrated solution to significantly change the boiling point by enough for it to make that big of a difference for your cooking. They're going to measure the concentration for these types of things in something called molality. That's going to be the number of moles dissolved in a kilogram of solvent instead of in a liter. So molarity, we use liters of solution. In molality, they use kilograms of solution. For our purposes, we're using water. It's going to be the same as molarity because water, 1 liter, has a mass of 1 kilogram. Our molarity and molality will be interchangeable as long as we're using water for our solvent. Some of you are going to go on in chemistry in college, and then molality will be an important factor. So I just wanted you to have heard it ahead of time. For right now, it's not going to be a huge deal. Ionic compounds dissociate. We talked about that earlier. So solutions made with ionic compound will have a bigger effect on the boiling point than covalent compounds will. They also do something else. We say that they can conduct electricity, and so we call them electrolytes. Electricity is the flow of electrons, and electrons have a negative charge. So if you have a neutral substance, there's nothing to help push or pull the electrons through. So if I just have solid sodium chloride over here that's neutral, there's nothing to help move those electrons. But if I have my aqueous sodium chloride, where I have positive sodium ions, the positive sodium ions will attract the electrons because opposite charges attract. The negative chlorine ions will push the negative electrons because like charges repel, and that will help the electrons flow through. So anything that's going to have areas of opposite charge in them are going to work really well as conductors of electricity. So our ionic solutions will conduct electricity really well. They're electrolytes. All right, let's take a look at what we mean by dissociate again. So we talked about this before. Ionic compounds are going to dissociate, so that means they're going to break apart into the ions that they're made out of. Remember, if we have a binary compound, so there's 2 capital letters, it's going to split in half where the capital letters are. The first half is your positive ion. You look up its charge in the periodic table. The second half is your negative ion. You also look up its charge in the periodic table. So for every 1 mole of this KCl that I put in, I make 1 mole of potassium ions plus 1 mole of chlorine ions for a total of 2 moles of particles. If I have magnesium chloride, again I'm going to split this in half right here. So I have 1 mole of magnesium chloride splitting into 1 mole of magnesium ions plus, look what happens, each of these chlorine ions becomes its own separate chlorine ion. It doesn't stay hooked together in 2 pieces. So I end up with 2 moles of chlorine ions for a total of 3 moles of particles. So magnesium chloride would have a bigger effect on the boiling point than potassium chloride because it's made of more pieces. Be careful with that more pieces part though, because when we look down here at this ammonium sulfate, this is a ternary compound. How do I know it's ternary? There's 1, 2, 3, 4 capital letters. So it's going to split apart here where my polyatomic ion is. So for every 1 mole of this ammonium sulfate that I dump into solution, I have 2 sets of ammonium, so 2 moles of those particles, and 1 set of the sulfate for a total of 3 moles of particles. The polyatomic ions stay bonded together. The polyatomic ions do not split apart, they stay bonded together. Remember that, because this magnesium chloride and the sodium sulfate would have the same effect on our solution, even though it looks like the ammonium sulfate is made of more pieces. Molecular substances are going to be things made with all nonmetals. Molecular substances made with all nonmetals. Typically, the most that we're going to look at are organic compounds, so things with carbons and hydrogens and oxygens. They do not conduct electricity. They are not electrolytes because they do not dissociate. They will not come apart. The way that they're held together keeps them together even in water. So our sucrose here does not break apart into carbons and hydrogens and oxygens. It stays put together. How will I know whether it breaks apart or not? Is it made with a metal or a polyatomic ion, or is it made with all nonmetals? Remember, the nonmetals are hydrogen and everything on the right. So if it's made with only nonmetals, it will not dissociate. These are tricky ones. This is an alcohol. The alcohol looks like it has a hydroxide polyatomic ion in there, but that OH is not considered a hydroxide. They call it a hydroxyl. And the way that it's holding on to the carbons in this compound won't let it dissociate off. Since it can't dissociate off, it's not a hydroxide ion. It stays hooked on as a hydroxyl, and it will stay together in this piece. So what you're really looking for is if it's made with all nonmetals, it's not going to dissociate. 1 mole of sucrose in my solution gives me 1 mole of dissolved sucrose particles. 1 mole of ethanol in my solution will give me 1 mole of ethanol particles. Will they raise the boiling point still? Yes. But if I'm comparing sodium chloride to sucrose, the sodium chloride is going to raise my boiling point more. So your order, if you're looking to see which is going to change the boiling point the most, it's going to be an ionic compound before a covalent compound. And it's going to be the ionic compound that's made of the most pieces. Freezing point depression, the same as boiling point elevation, except we're lowering the freezing point, and it actually has a bigger effect. That water particle is trying to hook itself back up together into a pattern to become a solid. So having those other particles, those non-volatile solutes in there, interrupt that pattern. They have to kind of get shoved out of the way so the particles can make their pattern. So it has a greater effect on the freezing point. So if I add 1 mole of particles to water, his new freezing point has to be negative 1.85 degrees Celsius. And you have an ionic compound. We use sodium chloride on our roads in the winter. So you make your sodium and your chlorine ions. So we have 2 moles of particles. You're going to have a greater effect on the freezing point if I have just 1 mole of sodium chloride in my solution, 1 molar solution. It has 2 moles of particles. My new freezing point is going to have to be negative 3.7 degrees Celsius. So when the people on the roads department look at the weather forecast, they can see how cold it's going to be outside, and they change the concentration. They use salt and sand, typically the salt to help lower the freezing point so that the ice melts, and the sand for traction so that you're not sliding on the wet, slippery roads. They look at the temperatures, they look at the weather forecast, and they decide how much salt they're going to mix in with that sand. They want to use the least amount possible because it's damaging to the roads, it's damaging to cars, and it's expensive. They want to try to keep it cheap. Okay, so if we are dissolving 1 mole of NaCl in a kilogram of water, how much does it lower the Celsius freezing point? Well, it lowers it by 3.7 degrees Celsius because your sodium chloride splits into 2 pieces. How many would that be in kelvins? Trick question, right? It's going to be a change of 3.7 because the size of a calcium is exactly the same as the size of a degree Celsius. Last thing is some practice problems using colligative properties. What types of things will they ask me on my test? So let's read this first question. The first question says, why is calcium chloride used more effectively to eliminate ice from smaller areas such as sidewalks? How many degrees Celsius will the freezing point of a 1 mole calcium chloride solution be lowered? Now remember, I told you they're going to use mole because we're technically measuring this in kilograms instead of liters, but that is the same thing, so don't be confused by that. Let's take a look at calcium chloride. They gave us an equation. The calcium chloride, CaCl2, binary compound, we're going to split it right here. So for every 1 mole of calcium chloride, we make 1 mole of calcium ions and 2 moles of chlorine ions for a total of 3 moles. So for the part 1 of this question, why is it more effective? Well, it makes more moles of particles. And the part 2 wants to know how much it would lower it by. They no longer put this freezing point depression number on your reference table. So if they want you to do this question anymore, they're going to have to tell you it's 0.185. Don't feel like you have to memorize that because you don't. So for the part 2, I would take my 1.85 and multiply it by the 3 moles. And of course 15 and 25. So it would change it by 5.55 degrees Celsius. So our new freezing point would be negative 5.5 degrees Celsius. Okay? The more particles it turns into, the lower it drops the freezing point. I've seen this also with an environmental slant. They want to know why, if calcium chloride is safer for the environment and less damaging to the organisms that live in the ditches and the sides of the road, why do we use sodium chloride instead of calcium chloride on our roads? And the reason is generally because it's cost effective. The calcium chloride is very expensive. All right, multiple choice questions. Which ratio of solute to solvent could be used to prepare a solution with the lowest freezing point? If you want the lowest freezing point, you want the most concentrated ionic one. Because if 100 grams, 1 gram and 100 grams are all 100, they're all 1 gram of solute, 1 gram in 100 or 1 gram in 1,000. Well, the 100 is going to be more concentrated by default. Sodium chloride, ionic, it's going to dissociate into 2 pieces. Glucose, covalent, it's going to stay together in 1 piece. So between the two, your ionic is always more effective in lowering the freezing point. So there's your answer. Most concentrated ionic solution. And this last question with the flasks show us 4 different types of solutions here. This first one, KCl, binary compound, metal and a nonmetal, so that's going to be ionic, which means it's going to dissociate into potassiums and chlorines. CH3OH, all nonmetals, so this one's going to stay together. That's covalent, and it's going to stay together as 1 piece. Barium hydroxide, polyatomic ion, so it's ionic. It's going to split apart right there into 1 barium and 2 hydroxides. And this one's kind of tricky. This guy is actually an organic acid. And we haven't talked about this yet, so I'm just going to show it to you here. Organic acid. This guy pops off as an H+. So this is actually going to split into 2 pieces. You're going to have the CH3COO negative and the H+, so it's going to break into 2 pieces. And I'm just going to tell you that now, and I won't ask you this question until after we've talked about acids and bases. But don't forget this question. Really large hint. Don't forget this question. All right, question A wants to know which solution contains electrolytes. Well, anything that's going to split into pieces that have charges are going to be electrolytes. So the KCl splits into pieces with charges. The BaOH2 splits into pieces that have charges. And our acid splits into pieces that have charges. So the only one here that's not the electrolyte is this covalent compound. Next question wants to know which one has the lowest freezing point. So the lowest freezing point will have the most number of particles. That's actually your explanation. So explain your answer. The one that has the most number of particles when it dissociates is going to be our answer. We just have to pick that out. KCl has 2 pieces. Barium hydroxide makes 3. And our acid only makes 2. So our answer is going to be the barium hydroxide because it makes the most number of pieces. And again, this question is not going to show up on a test until we've done a few more units. You'll know how to split these things apart and count their pieces. You'll know which ones are acids and which ones are not. By the time you see this on a test, you'll know what acids and bases are. You'll know what covalent compounds are. So just keep this one in mind and see how I walked through the problems. We'll do more practice in class, and that wraps up solutions.